Yeah. So the starting point of the talk is going to be a finite dimensional system. And so A and B here are matrices, and x0 is just some initial value. For this system, there exists a constant C such that you have something like an L2 to L2 boundedness. This is equivalent, it can be easily shown to A being a Hurwitz matrix, that is, all the eigenvalues of A have negative real parts. This is something one can easily show. And what Sontag did in 98 was that he considered the systems of the form x dot is equal to fxu, where f is a continuous Lipschitz function, locally Lipschitz for bounded u, and u is a locally essentially bounded function. For these systems, he analogously considered the condition that there exist comparison functions alpha, gamma, and kappa. Here, let me just recall K infinity is the space of comparison functions which are continuous, strictly increasing, unbounded, and gamma 0 is 0. Oops, the equal to 0 is missing here. Sorry for that. So, but I think the easiest thing to think about here, and especially since it's analogous to the above condition, is to think about the square function. So gamma x is equal to x squared is the easiest to think about. So here he considered the condition that for each input u and initial value x naught, we have this similar sort of L2 to L2 boundedness. So you have a gamma function here. So for each input u, you get that x is also back in, if you think of as again L2 functions, then this is again an L2 function. So you get L2 to L2 boundedness for each time t greater than equal to 0. And what does the theorem say? The theorem says that this condition is equivalent actually to the system being ISS, which means L infinity to L infinity boundedness in that case. So this was considered by Sontag in 98. And when I met Andre in Klagenfurt, our aim was basically to study the analog of this for infinite dimensional linear systems. And this is what we wanted to do. This is how we started. And so let me show you how we went about it. So to go about it, first we looked at what is known for ISS in infinite dimensional. So let's look at the setting first. Now we have an infinite dimensional system. So again, we have an AB system, but here A and B are no more matrices. But in fact, X is here a Banach space, and A is the generator of a C0 semigroup on X. Now, a C0 semigroup is a family of bounded linear operators, which has nice properties, nice continuity properties, and algebraic semigroup properties. But the main thing about this family being a semigroup and A generating a semigroup is that the Cauchy problem x dot is equal to AX has a mild solution, and the mild solution is given by these semigroup operators applied to the initial value x naught. So this is equivalent to A actually generating a C0 semigroup. The Cauchy problem has a mild solution if and only if A generates a C0 semigroup. And in the easiest case, you can think about A being a bounded operator or even in particular a matrix. Then, of course, we know that the solution of the Cauchy problem is given by the matrix exponential or the power series. So semigroups are a generalization of the matrix exponential. In general, of course, in infinite dimensionals, A would be an unbounded operator, and you cannot expect boundedness anymore. Okay, let's go back to our AB system. So A, we have seen, generates a semigroup. B is now a bounded operator from some Banach space U to the extrapolation space of X. And what is the extrapolation space of X? It's defined as the completion of X with now a norm given by the resolvent applied to X. So we fix some lambda in the resolvent set of the operator A, and we define this norm, and then we complete the space under this norm, and then we get our extrapolation space x minus 1. And it's irrelevant here which point in the resolvent set we take, because all these norms turn out to be equivalent. And usually for simplicity, we just assume that 0 is in the resolvent set, so we can just take A inverse x to be the norm. So that's what we usually do. And in this case, the nice thing is that the semigroup extends to a C0 semigroup on the extrapolation space as well. And the generator would be an extension of the A on the extrapolation space. So we get a C0 semigroup on x minus 1, which now helps us to get a mild solution of our AB problem using the variation of parameters formula. So if U is an L1 log function, then the system has a mild solution in x minus 1. So here xp is ct x naught, the initial value x naught. This is of course in x. T minus 1 is the extrapolated semigroup. So since B maps U to x minus 1, T minus 1 remains in x minus 1. So this term is a priori in x minus 1, and hence we get a mild solution in x minus 1. And usually we denote this integral by phi tu. So phi t is called the input operator. And in general, phi t u belongs to x minus 1 because B maps into x minus 1. This is the general setting that we have in our infinite dimensional setting. And in order to study ISS, so I go back, I just restate what our setting is for our AB system. In order to define ISS, we need to first define something called LP admissibility. So we've seen that this phi tu a priori lies in x minus 1. But in case it maps into x, so if the range of this input operator is x, then the B is called an LP admissible operator. Your P can be any number from 1 to infinity inclusive. So it's irrelevant here. So whatever P is called LP admissible if the input operator maps into x. And this by closed graph theorem is just equivalent to phi t being a bounded operator from LP u-valued functions to x. So if you have a bounded operator, phi t is a bounded operator from LP u-valued functions to our Banach space x, then B is called LP admissible. And then, of course, in this case, for each time, we get a constant CT, which depends on the time. In case this constant is independent of the time, if we can choose an independent time-independent constant, then B in this case is called infinite time LP admissible. So here, this B LP admissibility is sometimes also called finite time LP admissibility to differentiate between finite and infinite time. And now we define LP-ISS. So LP-ISS is defined as, first of all, we assume that sigma AB has a solution. So there is a solution, x-valued solution for all times t. And we have comparison functions beta and gamma. So gamma as before is the continuous, strictly increasing, unbounded functions, gamma 0, with which are 0 as 0. And KL, I forgot to mention it here, is the space of functions which map from, so they are defined from R2 plus to R plus, and they are increasing in the first component and decreasing to 0 in the second component. So strictly increasing in the first component and decreasing to 0 in the second component. And for simplicity, you can think of, so beta x norm x naught t as, if you want an example, exponential to the power minus t times the norm of x naught. That's a simple function to think. Okay, so then we have we call the system LP-ISS if you get boundedness from, so U is an LP function as here. So this is the norm of U in LP because we're talking about LP ISS, and we a priori assume that there are solutions in X, so we can talk about the norm of XP in X. Okay, so let's explore LP ISS further. So if you look at this condition star and you substitute the initial value x naught is equal to 0, then whenever norm u is equal to 1, if the LP norm of u is 1, then we get that phi tu, because if x naught is 0, then xt is just phi tu, and so the norm of phi tux is less than gamma 1. So this implies that B is in fact infinite time LP admissible. Note that since we assume that xt belongs to x for all t, that of course a priori means that our assumption includes LP admissibility, because if xt is in x, in particular phi tu is in x. And so LP admissibility was the part of our definition. But in fact, if we have LP ISS, then we here saw that we even get infinite time LP admissibility, because now the constant here is independent of time. Secondly, if we substitute u equal to 0 now, then what we get is xt is that norm of tt is strictly less than 1 for large t, because beta was a comparison function in KL, and that means that it's strictly decreasing to 0 in the second component, so in the time component. That means that you can make for large times t, we can make the norm of the semigroup operators to be strictly less than 1. This implies that actually the semigroup is exponentially stable, which means that there exists constant m and alpha greater than 0, such that norm of tt is less than m e to the power minus alpha t. So this is the reason why I said to just think of beta as the exponential function times the norm of x naught, because for linear infinite dimensional system, this is what we actually get. Of course, what we notice is if we had infinite time LP admissibility plus exponential stability, so this condition, then by triangle inequality, we would also have LP ISS, where beta would be this m exponential minus alpha t times norm x naught, and gamma norm u would just be the constant coming from the LP admissibility, so this constant. So what we basically observe is that LP ISS is equivalent to the exponential stability plus infinite time LP admissibility. So this is what we just saw, that LP ISS is equivalent to exponential stability of the semigroup plus infinite time LP admissibility of B. And that's a simple observation, as we saw. This was the observation was nothing complicated. But what is actually more true, so even more we have that the exponential stability and infinite time P admissibility is also equivalent to just LP admissibility and exponential stability. So basically for ISS, it's sufficient to show exponential stability plus finite time admissibility of the semigroup. And this was shown by Birgit Jakob, Robert Nabulian, Jonathan Partington, and Felix Schwenninger in 2018. And this result was mainly the starting point for us. So we wanted to study integral ISS, so the generalization of what Sontag did in infinite dimensions. And our idea was that we define the integral to integral ISS, and we show it to be equivalent, or we hope to explore its relation with exponential stability and a generalization of LP admissibility. And this means, so of course, as in the definition of LP ISS, P admissibility was already included. So in order to define integral to integral ISS, we first need to study a generalization of LP admissibility. So that's what is the first step, and that's what the first thing I show you here too. So again, I just restate our setting of the system sigma AB. And now in order to define LP to LQ admissibility, so we integral to integral, what we did saw earlier was L2 to L2 in the finite dimensional setting, and then Sontag generalized it with using comparison functions. And in general, you can of course talk about LP to LQ for any P and Q. And so let's just recall that the LP admissibility is defined as boundedness of the input operator from the space of LP functions, U-valued LP functions, to the Banach space X. So more generally, if we want to define LP to LQ admissibility, no points for guessing, it's the boundedness of the operator from LP, U-valued LP functions to X-valued LQ function. So instead of it mapping into X, what we are asking it is that phi tu is, we now have an LQ function. So yeah, the input operator maps into LQ valued X function. Of course, this does not mean that phi tu must be in X for each X, because if for it to be in LQ, it's sufficient that it is there for almost every T. And this means that, and since the time need not be uniform in U, this means that this does not include LP admissibility. So of course, so my point is that LP LQ admissibility does not a priori imply LP admissibility. So it's a more general notion. And just like we defined infinite time LP admissibility, which was that these constants are independent of time, we do the same for LP LQ admissibility because we can. So if the constants can be chosen independent of time, then we call B to be infinite time LP LQ admissible. Okay. And analogously, what we can also define is LP to C admissibility. By C, I mean the space of continuous function. So of course, that would be X-valued continuous function. So one can similarly define, instead of taking here the LQ norm, the norm in continuous function, so supremum norm. And we analogously get both the definition of LP to C admissibility and infinite time LPC admissibility. Let's look at some simple implications of these properties. So first of all, what Weiss had showed in 1989 was that if P is strictly less than infinity, then LP admissibility always implies LP to C admissibility. Of course, he did not use the notion of LP to C admissibility, but what he basically showed that if you have these LP admissible and P is strictly less than infinity, then the mild solution is continuous in time. And that that is equivalent to it being LP to C admissible. That's just the definition. So one direction needs P less than infinity, but of course the other direction does not need P less than infinity, because if it is LP to C admissible, if the operator is even maps into the continuous function, then in particular it needs to map to X. So so the other direction, the converse direction, is true for all P, and it's trivial. But the forward direction was shown by Weiss in 89 for P less than infinity. Now, if we have LP to C admissibility, that means that the input operator maps LP to the space of continuous functions. And because we are working with bounded intervals here, so the space of continuous functions maps into the space of LQ functions. So LP to C admissibility is of course stronger than LP to LQ admissibility. Once you map into continuous functions, you also map into all the other LQs. And again, because we are working with bounded intervals even for the LP case, so what you can actually do is for P, you can go up, and for Q, you can go down, because you can start with a smaller P, no, with a larger P, but with a smaller LP space, and you can end up in a large LP space. So L1. So this is just easy to see from the boundedness of the input operator and the LP-LQ inclusions. Okay, so now we have defined LP to LQ admissibility, and as we saw before that LP ISS is equivalent to exponential stability plus finite time P admissibility. Our hope was that we just define LP to LQ ISS in an analogous way, and hope that we get it's equivalent to exponential stability plus finite time LP-LQ admissibility. And this basically boils down to showing that for exponentially stable semigroups, finite time LP-LQ admissibility implies infinite time LP-LQ admissibility, just like in the P admissibility case. So then we wanted to examine LP-LQ admissibility more, and it turns out that here the situation is not as nice, and even for bounded operators. So if we consider a simple system, x dot equal to minus x plus u, then your semigroup is of course just e to the power minus t, and your operator b is just the identity operator. So b is a bounded operator, which means it's admissible, of course. It maps into x. And your semigroup is also exponentially stable. It's literally e to the power minus t. So this is a very nice situation. And in this situation, we can directly write what phi tu is. And once we write the input operator, it's easy to see that it maps LP to the space of continuous functions. The integral is continuous. It's easy to see. So B is LP to C admissible. And that implies that it's LP to LQ admissible as well for each P and Q. So the finite time LP to LQ admissibility is guaranteed for all P and Q. It's a very nice system. But now if we start with a P which is strictly larger than 1, then you can choose U, which is an LP, but not an L1. And for simplicity, we choose U to be a function which is positive almost everywhere. This can be done because P is strictly larger than 1. Then we integrate our system. So with initial value x0 is equal to 0, if we integrate here, then we simply get that the integral of x is nothing but minus xt plus the integral of u. And since u was not an L1, this term here, the second term, the integral of u converges to infinity as t tends to infinity. But what about xt? Now xt depends, of course, on u. But what our nice situation even tells us that the system is LPISS, exponential stability plus admissibility. That means it has bounded energy convergence state property. Basically, that means that xt converges to 0 as t tends to infinity. So now this goes to 0 and this goes to infinity, which means that our integral of our state is not bounded as t goes to infinity, which means that the input operator does not map into L1. So our solution does not lie in L1. So B is not infinite time L1 admissible, LP L1 admissible. So, but it was of course LP to L1 admissible. So for the point is that for LP LQ admissibility, even under exponential stability and for the bounded case, the finite time and the infinite time are not equivalent in general. However, here actually as B is a bounded operator, we can show that LP-LQ admissibility is infinite time if P is smaller than equal to Q. So it doesn't work if P is larger than Q, but it does work if P is smaller than equal to Q. And the proof of this is just actually a simple application of Young's inequality. I'm not going to do that here. But basically, what I wanted to do with this example is to show you that it's not reasonable to expect that LPLQISS, what we are going to define, is equivalent to finite time LPLQ admissibility and exponential stability. So for the integral to integral case, the situation is not as nice as just the ISS case. Okay. So while we are talking about LP to LQ admissibility, and before I move on to the integral to integral ISS, let me actually talk about something called maximal regularity. Maximal regularity is like a well-studied topic in functional analysis. And it turns out it's quite related to what we've been talking about, the LP to LQ admissibility. So let me show you what maximal regularity is. So for maximal regularity, we now consider a system sigma AF. So instead of an input operator, linear operator B, we just have simply a function f in time here. And here we can either work with a bounded interval or the half rate. So I is either a bounded interval 0t or just r plus. Then the maximum LP regularity is defined as follows. If we have a constant which depends only on the interval, so not on our initial value f, such that for each f in LP, x-valued LP function, there exists first of all, this system has a strong solution x, and the strong solution satisfies the following, that both the solution and its image under the operator A lies again in LP, and you still get boundedness with respect boundedness. It's still the norm is strictly less than norm f times p, of course, with the constant c. So you get, the point is you get as much regularity as f has. So you get the best possible regularity for x dot and ax. Now, how is it related to what we've been talking about? First of all, let me talk about some well-known facts about maximal regularity. So maximal regularity actually ensures that A generates a C0 semigroup. And not only it's just a general semigroup, it's actually a very strong semigroup. It has something called an analyticity property, or it's also called holomorphy. And so maximal regularity on Banach spaces always implies that A is associated to an analytic C0 semigroup. Secondly, a very strong result is that maximal regularity is independent of P. If P is strictly between 1 and infinity, so that means if we can show maximal regularity for one of these P's, then that implies for all other P's in this open interval. Thirdly, and this is where it comes how all of this is related to LP-LQ admissibility, is that maximal regularity is now equivalent to a boundedness condition. That is, there exists C, so the C is same as here, depending only on our interval I, such that we have boundedness of this convolution operator with respect to F. So now if you just remember what our input operator was, this looks a lot sufficient because here we have the semigroup. Then A minus 1 is the generator of the semigroup on X minus 1, the extrapolation semigroup. And F was in LPIS. Yeah, IX, sorry. And if you just replace A minus 1 with B, then what we observe is that this is just the LP to LP admissibility uh, of the operator A minus 1. So basically maximal regularity on bounded intervals. So if I is a bounded interval, then maximal regularity is equivalent to just LP to LP admissibility of the operator A minus 1, which maps from uh, x to x minus 1. And in case I is R plus, then you get infinite time LP to LP admissibility of A minus 1. So basically, LP to LQ admissibility is just a generalization of a very well-known property, maximal regularity, where we generalize the operator from A minus 1 to any operator B mapping into X minus 1, and also we let P and Q vary. And using these well-known results of max regularity, so either using the results directly or using the proof technique, what we could show is that if our semigroup is exponentially stable and analytic, then we do get that the LP to LP admissibility is equivalent to infinite time LP to LP admissibility for P less than infinity. So if your semigroup is exponentially stable, that's not sufficient. You also need to a priori assume analyticity, and then you get that LP-LP admissibility gives you infinite time LP-LP admissibility as well. And moreover, using the second fact, we can show that that for analytic semigroups, infinite time LP-LP admissibility and LP-LP admissibility both are independent of P. So if your P is equal to Q, then it's irrelevant where P and Q are in between one and strictly between 1 and infinity. So one implies the other. Are there any questions so far before I go to my last slide? I guess not.
Okay, maybe my question will be, what do you mean under independent of P? So do you mean that if it is LP admissible for some P, then it will be for the others? Or you have also some for your constants that you can choose uniform constants?
No. I just mean that if it's admissible for some P, then it's admissible for all P.
Okay.
Yes,
fine.
That's
Thanks.
what I mean by independent. Okay, great. Thanks for the question. And then let's go on to LP, LQ, ISS, or the integral to integral ISS, which was the topic of the talk. And as always, the system is just as before, the sigma AB system. And let's recall what LP-ISS was. So LP-ISS was if B is LP admissible because we assumed that the solutions exist, lie in X, and an inequality with the comparison functions. And using this, we can just generalize and define LP-LQ-ISS. So if we want to define LP-LQ-ISS, instead of LP admissibility, we assume it's LP to LQ admissible. So the solution lies in LQ. And we assume that there are comparison functions sigma and gamma, such that the LQ norm of our state is bounded with the initial value and also the LP norm of our inputs for each time t greater than equal to 0. Now, since we have linear time invariant systems, the question is, do we really need the comparison functions, or as in the LP-ISS case, could we just do away with them and get some constants? So again, that's easy to see here as it was before. So what LP-LQ-ISS tells us, if we put x naught is 0, so if the initial value is 0, then as before, the supremum of the input operator applied to u, now not in the x norm, but in the LQ norm, is smaller than some gamma 1, which implies infinite time LP-LQ admissibility, because now the constants are independent of time. Also, what it implies, if you put u equal to 0, then you get that the LQ norm of the semigroup applied to x naught is less than infinity for each. Okay, this should be x naught in x and time t. And because the reason I assume q is less than infinity is that a famous result of Datko and Pazzi tells us that if q is less than infinity, then this condition is sufficient for the semigroup to be exponentially stable, which means that there exists m and omega such that norm tt is less than m e to the power minus omega t. And now if you actually compute the LQ norm, then basically you can estimate it from above by the LQ norm of this exponential times norm x naught. And this is bounded from above by 1, the LQ norm. So actually you get m times norm x naught from LP to LQ ISS. So let's see what we have. From the first implication, we get that is infinite time LP to LQ admissible. And from the second chain of implications, we have that the sigma norm x naught, we can just choose to be a constant times norm x naught. And of course, we already got exponential stability on the way. So what we've observed, and since the reverse direction was even more trivial, so what we've observed that if q is less than infinity, then LP LQ ISS is equivalent to exponential stability plus infinite time LP LQ admissibility. And using the results on max regularity that I showed you, we could even show more, is that for analytic semigroups, LP ISS is independent of P. Again, this means that if it's LP ISS for some P, then it's LP ISS for all P. And for P less than infinity, LP ISS is equivalent to exponential stability plus LP admissibility. So we don't need to show infinite time anymore. If the semigroup is analytic and P is equal to Q, then exponential stability plus finite time LP admissibility is sufficient. In fact, if we have a Hilbert space, then we could even show that we can get away with admissibility. We get it free of cost. For analytic semigroups on Hilbert spaces, we can get admissibility free of cost. And this is also something we showed using the methods from using the techniques of maximal regularity, because for C0 semigroups on Hilbert spaces, which are analytic, maximal regularity is equivalent to exponential stability. And that's where I stop, as promised, before time.